Dr. F. McNeil Cheatwood has played key roles in NASA's planetary atmospheric flight efforts for the last 30 years. He is the agency's senior technologist for planetary entry, descent, and landing, or EDL. At the Langley Research Center, he has led development of technologies and systems for advanced planetary EDL in support of NASA's robotic and human exploration missions. From 2007 to 2009, he was the hypersonics project scientist for NASA's Aeronautics Research Mission Directorate, where he defined an investment portfolio featuring inflatable aerodynamic decelerator, supersonic retropropulsion, and advanced ablative thermal protection system technologies. He served a similar function from 2010 to 2012 as the EDL principal investigator for NASA's Space Technology Mission Directorate. He was the PI for the Mars Science Laboratory Entry, Descent, and Landing Instrumentation, or MEDLEY project, with a Mars entry in 2012. He leads NASA's efforts to develop hypersonic inflatable aerodynamic decelerator, or HIAD technology, and served as the PI for the program to advance inflatable decelerators for atmospheric entry, HIAD project, and inflatable reentry vehicle experiment, or IRVE flight tests. He is currently the PI for the low Earth orbit flight test of an inflatable decelerator, or LOFTID, which will fly just a little bit later this year, November. And on a personal note, he's a great guy to work with and for. So I'm sure we are all giving you a warm welcome, Neil. And I see your slides. So if you are ready, the floor is yours.
Well, thank you for the introduction, Adam. I really appreciate the opportunity to present to y'all. Thank you, Adam, and also Dave Schuster for asking me. So with that introduction, I'll just jump into this. As you've already kind of told me what we're going to talk about. So HIAD technology, what's the idea there? What we're doing here is trying to come up with a way to have larger aeroshells available to us when we go to destinations, whether it be coming back to Earth or going to Mars, or basically any place in the atmosphere. So the idea is to replace the traditional metallic or composite rigid structure with a deployable structure. But if you're going to bring that in from outside the atmosphere, then you also need to replace that our traditional ablative rigid TPS, whether in the form of tiles or honeycomb, or even reusable tiles. All those rigid things we're replacing with a flexible heat shield. And so in these photos, you can see real quickly, and let me see if I can get my cursor. Yeah, I think I figured that out. So here's an example of a structure. This one's sitting in our vacuum tub. We actually can drape this with plastic and pull a vacuum on it and load these articles in a static fashion to get an early read on their performance. So this is the structure by itself. Here we have the structure with the a flexible TPS on top of it. Here's a earlier 6-meter article that we put into the INFAC facility. Fortunately, we had some of our not as tall engineers, vertically challenged engineers there, so it looks even larger than it really was. And over here then is actually the engineering development unit for our 6-meter LOFTID test. Quickly looking at the anatomy of this, it's more than a stack of tori. We also have to kind of lash those tori together. And so if you look over here, you can see how these two tori are coupled together, and then these two tori are coupled. Under here, you can't see it, but then we stagger it, just kind of like brick joints in a common bond brick joint. And so that makes the whole structure kind of act as one. Then we also add these radial straps, because otherwise, this first torus, you've got a strap here trying to pull everything out, and you got another strap going into the rigid structure. And so there's that shearing motion. And so by putting these radial straps with the chevrons on it, we can actually distribute that load. So that's basically the inflatable structure. Here is a Gen 1 system where we used Kevlar Technora. Here we've gone to a Xylon that can handle higher temperatures, and at that higher temperature, it also actually has more strength. The flexible TPS is a modular system. We have an outer couple of layers that have to resist the shear of the flow field and the heat flux. Then behind it, we put layers of insulator, depending on the heat load we're expecting. That kind of determines how many insulator layers we do. And at the very back, we need a gas barrier because all these materials in front are porous. They're either woven fabrics or they're felts or whatever. And so we need to have something in the back that kind of deadheads the flow. In our previous flight tests, we've flown a Gen 1 system for the TPS, that's Nextel outer layers with a stack of Pyrogel blankets and a Kapton Kevlar laminate. And the back face of this, similar to the structure, can handle about 300 C, 250 to 300 degrees C. Our Gen 2 system, we put a silicon carbide fabric on the outside. And then we've also gone to some other insulators that are more effective at the hold together better at higher temperatures. And then we put the Pyrogel, which is a very good insulator, in the back where it doesn't get as hot. And then we back that up with a new Teflon Xylon laminate, and that allows us to go up to 400 C and beyond. And as a point of reference, we design our current TPS systems basically for a 250 bond line temperature. So when we go to this Gen 2 system, which we're flying on LOFTID, we're now flying at the equivalent of a bond line temperature, much higher than what we do now. So why do we do the inflatable? Well, we're looking to increase the diameter, as shown in these lower left figures. And these are really old plots here. These are almost 20 years old at this point. But what we did at the time is we took the Mars Science Laboratory entry, which is, at the time was only 2,200 kilograms. It later went in at more like 3,300 kilograms, I believe. But at 2,200 kilograms, all we did was change that diameter in our post trajectory deck. And what did that do? Well, it knocked down our heating, and it increased the altitude at which we decelerated. And in fact, I should have said that the other way around, because the fact that we decelerate higher and encounter fewer molecules of the atmosphere is exactly why our heating goes down. So what does this mean? Well, an important thing is getting that heat flux that low means now we have materials that can handle these kind of temperatures. Inflatables are not actually a new idea. They were looked at in the 60s, as were the deployable decelerators. There was a lot of work done on them until we convinced ourselves that we could do a supersonic parachute deploy during the Viking development days. So, now we have, we got, fast forward, 40 years, and now we've got materials that can handle these temperatures. So that's a really important thing. What does this mean? Well, we're decelerating higher. So that means that we can land at higher altitudes on Mars, which is a real challenge for us. In fact, if you look where this parachute deploy kink is, and again, this was just a demonstration. It's not what we're advocating for anything, but this would basically let us land on Olympus Mons, which is the tallest volcano in the solar system, at least that we know of. So we can access more of the planet, and by being stowable, we can stow inside this volume and fit inside the launch vehicle shroud. Whereas over here, you can see the MSL and its 5-meter shroud, and it's kind of filling up most of it. We have been working this for about 15, coming on 20 years now. We started out with not very much money, so we did some ground tests, and then we did a flight test. We had a launch vehicle anomaly on the first one, but at the time I worked for the hypersonics project, and the PI really believed in this technology. He said, look, I'll fund a build to print reflight. And so we waited about a year for the mishap investigation board to tell us what we had figured out about 5 minutes after the flight. And then we were able to get started. So we actually built and launched IRVE3 in about a 15-month time period. That success, and this is an image of it here, that we had cameras on the back. You can see the Earth below. That success kind of propelled us a little bit. It was right when they were starting up the Office of Chief Technologist again, and funding projects, which now all fall under the Space Tech Mission Directorate. And so we got a HIAD project, which also included an IRVE3 flight test. And with IRVE3, we really went to more significant heating. Here's an image of that. We had cameras all around it on that one, so you can see the earth below after we reoriented. And then we kind of had a lull in funding. And so we just did some low-level ground testing and developed some of the elements of a 12-meter article. Here you can see a half dozen of us kind of lifting this thing over our head, so it's a fairly lightweight structure. And then now we're doing the LOFTID flight test. In those ground-based efforts, it wasn't just about testing something to failure. We really were trying to get to the fundamental physics of all the elements here, and so we did testing. We demonstrated the manufacturing first. Nobody had ever built a flexible TPS this big before. We've not really, worked with stacked tori like this before. Then we tested them. Some of them were elemental testing, like what we did at Armstrong. Others are at we did at LCAT or ArcJet testing. We've done hundreds of samples, different layups, different conditions, trying to understand where the corners of the envelope are. And then, ultimately we look at the system and assess its performance with testing. And ultimately we're trying to develop some high-end models that let us predict what's going to happen before it does. Here I'll just show a quick excerpt from a video you can get on YouTube. But this has an animation on the right and our video from the left. So the cameras are still inside there, and now we've ejected the nose shroud, and we're still stowed and pointing kind of away from the earth. So now we've released the restraint bag. We still haven't really started inflating yet. That's just the little bit of entrained gas there. And then we inflate, basically to full size. We need to get a couple of PSI pressure before atmospheric interface. But we want to ultimately, this one we took up to like 20 PSI. And then we had to repoint, otherwise we would come in backwards. We didn't have anything to right ourselves outside the atmosphere, of course. We had a lot of instrumentation on this so that we could assess the performance of the TPS. We even had a slight CG offset, and you can hardly see it in the picture, but what that did, that little shift gave us about an LRD of 0.2. So we came in, these are suborbital flight tests. When we go high in altitude, there's not a whole lot of energy. So we came at Mach 10 and saw about 15 watts per centimeter squared, which is about half of the capability of the Gen 1 system. But, you're looking at the video, when we hit 20G, you can hardly see much motion. And the other neat thing about this was we were able to fly from subsonic, from hypersonic through supersonic, transonic into subsonic with no drogue chute, no parachute. It was a theory I had that, since we had this sharp corner and no real aft body, that there really wouldn't be anything to drive the dynamic instabilities that we see on most every blunt body that we have to deal with. And sometimes that drives often that drives when we deploy the parachute or a drogue chute. So we were able to fly all the way through it, which I thought was a great thing. So after that, we started looking at these other missions. What would we do here? We have interest, and this is an old slide, but it does show kind of the range. The IRVE3 at 3 meters. We've got some commercial entities right now working with us that are looking in this range to bring small things back from low Earth orbit. We've got other missions that could benefit from these larger scale. We're working actively with ULA to bring back their Vulcan engine for their new Vulcan rocket. And that's going to require like a 10 to 12 meter. And then our big boy is the human Mars effort, where the studies inside NASA have shown that really, you don't have an option to go with a capsule because of that shroud constraint. You don't have an option to go with a mill-over-D just because of the mass. I mean, there's just not enough mass to carry the mass of the Aeroshell plus the mass of the payload exceeds the throw capability of the rocket. So this is something, we have been shining for the last several years. It seems like every time they do a study, we end up winning those. The fact that we don't have a back shell means that we've got to take that into consideration. The payload for impingement. So here's an oversized payload, and you can see how this was for the Mars study. You can see how the impingement's hitting here. But it turns out for some of our applications, we're finding, well, it's okay to have a little bit of impingement. Depends on what flight regime you're in and what pressures you see and what heat fluxes you see. And so for some of our applications, like the booster recovery, that's a suborbital flight test. And so the peak heating is like at Mach 8, which means it's basically not much heating. And so it's really not a driver for designing that, but the impingement we wanted to try to avoid, but it turns out, well, it's not that whole lot of impingement. That impingement turns out to be a riding force. So if you try to fly at angle attack to generate lift, that will try to push you back the other way. But it turns out for the particular application we're looking at right now, that riding force only means about, on the order of a degree angle of attack. So it's nothing that we can't manage. We also need to look at, the mass and the peak G load, because that basically drives our structure design. The heat flux determines whether we can fly that Gen 1 outer fabric or the Gen 2 outer fabric. And the heat load tells us how many layers of the different insulators we need. But since this is kind of a cafeteria menu type thing, we can pick and choose what Gen 1 elements or Gen 2 elements we want to fly. And as an example, on something like a suborbital return, the convective heating down into the bowl is not that large. So maybe instead of flying with Xylon, we go back to the Kevlar Technora. So you can see how we could mix a Gen 1 structure with a Gen 2 TPS. And even that Gen 2 TPS could have a Gen 1 outer layer. Let me tell you a little about LOFTID. Why are we doing it? Well, I mentioned earlier the heat load and heat fluxes. Well, I mentioned the heat flux is fairly low with a suborbital flight. The other thing is the heat load is as well. So if you look down here, we're looking to exceed 45 watts per centimeter squared, which is, maybe 2/3 of what our Gen 2 system can do, but it's probably more than our Gen 1 could handle. But certainly a significantly more energetic trajectory in terms of duration of that heat pulse. This 6 meter scale we're flying will be the largest blunt body entry ever, as far as I know. It's bigger than Apollo, it's bigger than Orion, it's bigger than MSL or Mars 2020, it's bigger than what Mars Sample Return is going to be. So this will be the biggest entry, rigid or flexible. And I think I'll just go to the next slide because I'm probably running a little behind here. So this is our ConOps. We're actually, for LOFTID, we're flying with a primary payload, the Joint Polar Satellite System, the second one, JPSS-2. So the ConOps is that they go into their typical primary orbit where they then jettison or deliver, I should say. Jettison doesn't sound good. They deliver their primary payload. Then they get out of that orbit, and then they turn us on. So we've been dead at that point, inert. We can't harm the payload, primary payload. So they turn us on, and they host us while we inflate the Aeroshell. And then they orient us in the proper direction and spin us up, release us, and then do a divert maneuver. And then our experiment begins. During that experiment, our Gen 2 system, one of the negatives about it is it's not radio opaque, so we can't get a lot of stuff transmitted through the heat shield. Instead, what we're doing is we're going to have a beacon transmitting up to the Iridium network, and it's just going to be a small subset of our data, but it will be something every 20 seconds or so, it'll try to send a packet that gets emailed down. We should be able to display that near real time, so at least we kind of see where we're flying within the corridor. On board, we have both an internal recorder and an ejectable recorder, and that's going to record all of our comprehensive data. That includes videos on the backside, 6 video cameras, 12 IR cameras. We'll get a full 360 view of portions of the tori so that we can get a heat map, a temperature map back there. That'll be great for CFDers to compare to. I think if you can compare down into a bowl on a non-uniform surface, you can probably handle most any weight problem. We also are collecting a lot of heat flux and thermocouple data, et cetera. And we will be going out and actually ULA has been a great partner here. So they provide the parachute system. They provided the boat barge, big thing. And we will go out and try to recover both the RV and the ejectable data recorder. So here's where we sit in the architecture. So this is the big J2 satellite, and we sit under it in a payload adapter shroud. This is our vehicle here. So after they release J2, then we release that outer part of the shroud, and then we inflate. And you can see here how small the area is that we're stowed into. And once we inflate, then we're released and we start our mission. So we're a passive entry. All we have for stability is the aerodynamics and the gyroscopic stability of a couple of RPM. Other thing I can mention is the inflatable tanks. It's not a trivial thing. The ULA also contributed those from their inventories. That's a long lead item that needs to be flight certified. So of course, stuff that they already fly on their system is flight certified. So that saved us a lot of effort. Here's the inflatable structure, getting its last touches before getting tested. So we have these strain gauges on it, tension gauges actually. And then here's our flexible heat shield that has been completed. Here's the nose cap for it with all the heat flux gauges and lift points, etc. Here we are in our complete system test that we just completed. So this is where we actually run end to end. Everything's on its own power. The computers are running it. So the first thing to do is we fire the cutters, and there's a cutter on this side and on the other side. So we want to make sure they both fired. Here we're just putting a little bit of gas in just to make sure none of the lines are kinked. We don't want to blow out anything. And then now we do the full inflation. So this is in a vacuum, like it will be. So it lets us test for issues with the electronics in a vacuum. It gets rid of the resistance of air in a vacuum, but we still have that problem of 1G gravity. So it's not going to be exactly what we see in orbit, but this is how how it inflates, and it's inflating at full speed. Of course, in 0G, it would take its shape a little faster because it wouldn't have the resistance of gravity pulling on it. And then I think it goes on to show, so the camera pods also, we wanted to make sure they were working. Now they actually have their protective lens covers on them, so you can't, you're not getting the beautiful view that you will get, but you can see they're all working. Although I'll say this one is probably not going to work. Fortunately, the video cameras aren't required for our level 1 requirements. So that's how we take shape. I've got a mission animation coming up that I'll show you if I've got, yes, I got time. Our hardware is currently on site at Vandenberg Space Force Base. Our launch date's November 1st. Things are proceeding well. And here is an animation. And I have to say that music's better than the cheesy stuff we had on our first RV video. I guess headquarters can afford better music than we can. I mentioned the instrumentation. I won't belabor this a whole lot, but a lot of pressure transducers on the nose. So we have a FAD system that'll let us isolate any motion between the inflatable and the rigid center body. And you'll be able to pull out, the alpha and beta and dynamic pressure. So the density that we're flying through real time for reconstruction efforts. Got heat flux gauges, including one of them being a radiometer, even though we're not expecting much radiation, but it's a freebie. We got some load cell pins, like I mentioned earlier. We're even flying a fiber optic stress system that goes under the nose cap, and we'll get a distribution of temperatures on the backside of the TPS. Got an IMU, GPS for locating it. Inflation system's got a bunch of instrumentation on it, so we can learn from that. The video imaging I've already mentioned, and then the comprehensive data. To wrap things up, I just wanted to kind of put this all in context. You know, what does LOFTID mean for the use of inflatables in the future? You know, way back when we did Project Viking, we didn't even know what the composition of the Mars atmosphere was, what the density was. You know, we felt like we were going to need to have a supersonic chute. You know, but they built a TPS that was way overqualified. It saw like 24 watts per centimeter squared. So we could have, you know, if we were to refly Viking, we could fly it with our Gen 1 system on top of the rigid Aeroshell. And then later with Pathfinder and others, we've kind of used that same TPS and at higher velocities and higher heat fluxes. But now we're kind of stepping away from, so, you know, with MSL, we had to switch to a different TPS. But my point is, Viking really led to all these missions. There weren't huge technology demonstration efforts. I mean, for Viking, there was $1 billion, and this is $1 billion back in, you know, 1970 dollars. It was $1 billion effort just for the technology stuff. So now where are we at with LOFTID? You know, we've done the IRVE3, we've got LOFTID. You know, what does that mean? Well, first, let's kind of put things to scale. So this is some of the finest parallel point engineering you'll ever see. So this 6 meters, a little bit bigger than that. And then we're talking about going to 10 to 12 and then 18. But you can see there are different entry masses and different velocities also, and different planets you're going at. So, you know, we can scale these things up or down as we need them. But LOFTID itself will, you know, certainly get us ready for a, you know, 6 meter or less LEO return. I probably would be comfortable going to 7 or 8 meters. I just, you know, it's not like we're at a cliff right now. As you go larger, there becomes issues with, all right, now how do we handle something this big? You know, as we lift the TPS over to the inflatable, will it even support its own weight, or do we have to set up some rigging for that? So, you know, that's of course means, you know, we probably want to do some risk reduction activities. And then obviously, if we're going to put humans on board, there's going to be a lot of risk reduction activities beyond LOFTID. So that's part of the overall things we have to look at. You know, increased scale is just one thing. You know, more efficient inflation systems. We're investing in multiple vendors right now through the SBIR process to come up with gas generator systems that would generate hydrogen, for instance, because that would give us the most, I shouldn't say bang for your buck. That is with hydrogen, that's always a, you know, kind of a explosive way to say it. But it does give us the most gas for the least mass, and that's very attractive to us for these missions to Mars. But for commercial applications, it might be we want to go with a cheaper solution because the commercial folks are going to be flying this over and over again. So those are the kind of things we need to do in the future. And I guess for that, I'll take questions, Adam.
Great, thank you, Neil. That was a great talk, great overview, and sure we're all going to be looking forward with anticipation in November to see LOFTID. If anybody has any questions for Neil, excuse me, please put them in the chat window.
And I'm not seeing the chat window since I'm in this. I guess I could get out of this though, or you can read them all to me, either one.
Not seeing